Imagine you are walking with your eye closed. You will be encountering obstacles and turbulences along the way. Once you reach an obstacle, like a wall, you then correct your trajectory to go around it. And this is basically what the wind turbine is doing today. A wind gust is the disturbance that the wind turbine encounters. The wind turbine will only react once the disturbance has reached the wind turbine by changing the blade pitch and the torque. Now imagine you can walk with your eyes open. You can now actually correct your trajectory before hitting the wall. For the wind turbine, this preview information of the wind field means load reductions and higher energy yield. LiDAR is like the open eyes for the wind turbine. You can see here an example of the wind measurement using a scanning LiDAR. Using the LiDAR measurement, you can anticipate the effect of the wind gust and change the pitch angle and the torque before the wind gust actually hits the wind turbine. In this lecture, we will look at application of LiDARs for wind energy. We will look at the measurement principle. We will look at 3 different applications of LiDARs and discuss the potentials. We will close this lecture with some reflections about the limitation of the LiDAR application. Our first question is, what is LiDAR actually? LiDAR is a laser instrument. It stands for light detection and ranging. Basically, it sends out light with a certain frequencies. This light will be backscattered by the little particles in the air, the so-called aerosols. The backscatter light will have a slightly different frequency than the original light signals. This is because of the Doppler effect that causes a frequency shift. By looking at the frequency shift, we can determine how fast the aerosols are moving and indirectly the wind speed. We need to remember 2 different important things of the LiDAR measurement. First, it measures the line of sight wind speed, which is the wind speed vector projection on the laser beam. Second, it's not a point measurement, but an average of the wind speed over a volume. So what can we do with this new sensor? We can, for example, improve the control of the wind turbine. Instead of the traditional feedback controller, we can design a feed-forward controller that anticipates the effect of the incoming wind and change the pitch angle or torque ahead of time. This can lead to significant reductions in the loading of the blade and the tower, as shown by the testing campaign at NREL. It was tested on the CAR 2 and CAR 3 wind turbine using the SWE scanning LiDAR and a commercial LiDAR. We can see that the feed-forward control was able to reduce the rotor speed variation up to 30%. This will also reduce the loading on the blade and the tower. This can be seen from the light blue curve on the power spectral density of the generator speed and tower bending moment in the figures. One of the problems that we encountered during the testing campaign is the hard target. Some of the signals were hitting a met mass. If these signals were not removed, the LiDAR will give a wrong estimation of the wind speed, and the performance using LiDAR was even worse than the feedback controller, shown as the red curve here. The blue curves show the reference feedback controller. What else can we do with the LiDAR? We can use the LiDAR to improve the power forecast of a wind farm. We can use the so-called long-range LiDAR that can look into the wind at distances up to 10 kilometers. We can use the information in the wind field to provide more precise power forecasts. This would give the grid operator about 10 to 20 minutes time to react to sudden changes in the power output of a wind farm. The ability to react ahead of time in an event of wind power ramp up or ramp down will be crucial for the stability of the grid. The third application that we are investigating is the use of LiDAR for wake steering. We can steer the wake of a wind turbine away from the downstream wind turbine so that we can actually increase the overall power of the wind farm. Now, the tricky part is that the wake is a very complicated phenomenon, difficult to predict with just models or simulations. By using LiDAR, we can get an idea of where the wake is actually going, the size of the wake. This valuable information for the wind plant controller, because this will close the loop of the control by using the information identified by the LiDAR. In this case, the LiDAR can estimate where the wake center is, and this can make the wake steering more precise. So, is the LiDAR the answer to everything? No. Just like any sensor or instrument, it has its limitations. We need to be aware of these limitations so that we can make a trade-off between the advantages and disadvantages of using LiDAR. First of all, LiDAR does not measure the 3D velocity vector, but the so-called line of sight velocity. We need to make some model assumptions to translate the line of sight wind speed to the horizontal and vertical wind speed. Second, the LiDAR has limited resolution in time. Typically, 1 Hz measurement is possible. But if we want to increase the spatial resolution by measuring at different points in space, the time resolution will be even lower. So understanding how to measure a representative effective rotor wind speed becomes very important. Third, the measurement quality depends a lot on the environmental conditions, whether there is fog, rain, low-hanging clouds. All these factors will have an impact on the quality of the wind measurement using LiDAR. Last but not least, people often mention the cost as a factor. Eventually, we will go down very fast once the early adopters of the technology can push the production costs down through standardizations and serial production. Adding LiDAR to the sensing of incoming wind speed will eventually change the way wind turbines are controlled. It will bring new cost reduction potentials, better wind power forecasting, improve the power performance, and reduce uncertainties in wake steering. Just remember, would you prefer to walk with your eye closed or open?